Hello friends, thanks for coming here after lunch, and I hope the music engaged you a little bit. Also what you just saw was completely AI generated. The text, the music, the vocals, so it's not my making to make this great AI tool. A company called Suno AI came up probably 2 months ago with something where you can actually create consistent music and actually extend the music so it sounds actually real. So that's where we are today. We are a little bit beyond what text can do, but however, most of our talk today will still deal with text. The talk is named UnleashGPT, Mastering the Implementation of Large Language Models. Setting expectations, we only have 1 hour. So I will try to introduce some of the concepts, but most of them hopefully with code samples. I have a lot of slides. I will skip over a lot of slides also. But I will try to ground the conversation a little bit with some of the concepts that are under large language models. Who of you thinks they have a good understanding of what large language models are and what's behind them, and why do we do them, and so on? Is there a lot of folks who are very experienced with this already? Not? A few? Okay. Well, then I will see you scoff or making faces during my talk maybe. So this happens when you deal with a company like OpenAI. Like on my flight to Portugal, I got the message that supposedly I had suspicious activity in my account. Since then, my main account of ChatGPT is closed. Don't worry, we were using mostly Azure OpenAI yet. And they still haven't been able, after now 36 hours, been able to tell me what exactly is wrong. Supposedly suspicious payment, it's $20 a month, every month. I don't know. I did some red teaming, but nothing too extreme. So just be a little bit aware if you work with a company like OpenAI. Surprising things may happen, and they may be sometimes difficult to resolve. Keep that in mind with all the excitement if you use it for something mission critical. Think about backups. So that was my experience. I've been on the conference trail for a while, in the industry also for a while, doing enterprise type of solutions for many years, but around 2014 I went back into combining it with information, innovation, virtual reality, mixed reality, cloud, applied artificial intelligence, and since about 2.5 years I've been playing with GPT stuff before most people cared for it. That's why I also have those MVP and regional director things, because I just talk a lot. Now, why do I show this slide? Just to contextualize where we're coming from and how do we interact with computers. In the 1940s, we would interact with the computers by literally rewiring them. Yes, this was our programming. Punch cards, a big innovation, and the integrated terminal. You could type in a computer, amazing. The mouse invented in 1963, the integrated keyboard, mouse, and graphical user interface introduced in 1968. Even touchscreens are from the 1960s, and smartphone form factors from 1992 and 1994 with apps with a Simon. So this is still how we interact with the computers. We learn, the computer expects us to interact with it in a specific way. We learn to speak computer. Now, the bigger picture that I see is that we're trying to move more away from that, and computers or IT in general, or the IT systems should understand more naturally what we want, our intent. And that is partially also, I think, what motivates a lot of the research going on into large language models. So I wanted to start with a really quick example. Of course, I forgot to start it up. It's something called Whisper. Whisper is by OpenAI also. And let's see. AI models, Whisper, and has been released as has been released as open source, and so people started playing with it. So what's cool about Whisper is, again, you can run it on your own computer because the model is available, right? So what can it do? For example, I could suddenly speak here and start speaking in Deutsch, weil ich spreche, eine Muttersprache ist Deutsch, und wenn ich Glück habe, wird das jetzt übersetzt werden? Okay, I'll give it one more try. Oh, I've configured the wrong microphone. That makes a difference. Hallo, guten Nachmittag. Ich hoffe, das Mittagessen war lecker. Hello, good afternoon. I hope the lunch was delicious. And then I'm going to the bathroom. So this is not a perfect implementation but that's in the app, because the app, what they didn't solve for you is how do you handle those audio chunks that you stream in, and so it comes up with weird things. But why do I show this to you? Well, because it's cool and you should download and play with it and do transcription and translation on your own device. However, the underlying paper that was published with it showed a really interesting finding. Whisper exists in different sizes, like a small size, very small size, medium size, large size, and in a version that only transcribes English to English, and one version that's multilingual, also able to translate, like from German to English. And they found that when the models get a little bit larger, still a size you can download to your computer, but a little bit larger, and measured in training budgets 10 to the power of 20-something, suddenly the multi-language model gets better into transcribing English to English than the model that was only trained of the same size, same training budget, that only has seen ever English to English. And that is so English to English model worse at transcribing English than multilingual model at a specific size. And those are things that we're seeing across this. This is a theme in large AI models, that suddenly they become better than you think in specific tasks that they haven't been especially been trained for in some of the specialty models. Yeah, so that could be then also summarization. That could be writing poetry. Could all be other things. Like a specialty model for poetry may fall behind a large language model that can do almost everything if the training set size is large enough. That's the current thinking. What is the latest in ChatGPT? Well, the latest would be Vision. I mean, I signed up for a new account. So now I could upload a picture here. Do I have a picture? My personal photos, koala. Oh, now we want koala rotated. And what's in the picture? So I upload this to ChatGPT, and ChatGPT suddenly is able to do something and describe that image. Again, how that works in too much detail we will not be able to get into, but that's kind of the latest innovation that came out with it. There's a large paper also associated with it from Microsoft, 140 pages, that looks very deep in what you can do with it. And you can already make more advanced things. You could like make a circle around the koala, make a circle around the person, write a number to it, and then tell me more about 2, like when the number is 2, and it would be able to do something with it. It can take like layouts of an app, for example. You take a picture of it and try to recreate it in code and all those magic things. So the speed of innovation is very, very fast. Another thing that it can do that's very, very late in the world of AI is so-called advanced data analysis, which is another trend that you see, that AI models can work with so-called agency. Agency meaning they can, they're able to do something. Like in this case, they have a little Python engine they can work with. Now, what can we do with this? We have here conf perfect solution. So I'm uploading some file, right? And so what's in the file? And that's a zip file, right? And I have no idea what is in the file, right? So what the ChatGPT now does, it's able actually to see, okay, the zip file, I can unzip a zip file because I can generate code for it, and then it actually executes that for you and can do something meaningful with it. It lists the file contents, and then Windows Form solution, Windows Forms app, oh, that's It contains a solution file, typically used with Visual Studio, and so on and so forth. And you could go on and on and on with that. It can inspect that. It can look into the individual files and even tell you the layout. It can change the layout in your app, all within things you just upload to it. Yeah, so this is some of the latest things that are happening, and a lot of effort goes into now what they call agent-based systems. So, which meaning like you give an agent some tools, and the agent can do something with those tools. Now, what is the foundation of all of that? The foundation of all of this is so-called tokens. So everything we interact with is a token. So here we have GPT 3.5 and GPT-4. When I write a text, hello in Porto to the NDC conference, then I go on, and all those colored letters here, each one is a so-called token, meaning a number. The number is what is passed to the large language model inside the representation of the text. Main purpose is just to make it smaller so that we don't encode letters, because we want to be more efficient in storing information, basically. And because it was trained on English, it is quite effective it has been optimized to be effective to encode the English language. When I write something in German, like Hallo zu der Konferenz in Porto, you see that, for example, the word Konferenz suddenly is 3 tokens, and meaning, as a side effect, when you work in non-English languages, it can get more costly because you work on tokens and pay by tokens. And also, even though large language models are getting really, really good and working with long text, still they maybe have more, they need to invest more of the internal brain power, if you want so, to work with longer text in non-English languages. Just keep that in mind a bit. Oops. So there's a paper around that. So the paper attention is all you need. Introduced the transformer model. The big innovation about transformers was that suddenly they were able to parallelize what before was only sequentialized. The RNN set were the default way how you work with natural language, basically did something like token by token by token by token, and when you needed to do so-called back propagation, you need to go all the way back, and you cannot parallelize that on large GPU clusters. That's one of the main motivations and innovations that the transformer architecture brought in, very simplified. And I will give you the slides later on. There's some great fun videos and how you can learn how transformers work internally. They have a smart way of encoding where all those tokens are, and then they're masking out with a matrix, basically, with matrix multiplication, things that the transformer shouldn't see, so it simulates in a way that there is a sequentiality in a sentence by doing matrix multiplications. The other thing is, one of the concepts in there is called attention. And you can visualize attention, right? You can visualize what those models do internally, theoretically, if it's small enough. The models, in the end, when they're done, are nothing like a big file, and the file describes weights, how different things are connected. Now, there are a few interesting things. For example, if you feed it, let's say, like a sentence here. Now, do we have an interactive? Klickerei here. Sorry about that. So basically, if you give like a model, like an input and an output, it basically assigns probabilities how things are connected, or weights. For example, here the word on is heavily connected between that and the end separator of a sentence. Yeah, in this layer 5, for example. In a different layer, things may look different. For example, here, well, let's find, of course, I may pick the wrong layer. Well, in this case, for example, here there's also a strong relationship to in this other layer. So all those layers combined try to represent all the concepts that the large language models extract from the real world, and you can somehow light up what happens in there if you for example, would give us contrastive pairs as a strategy. For example, a sad day and a happy day, then you may be able to find those parts in the model that get activated more often, and maybe those are related to some of those concepts like happiness or sadness and so on. But to make it a little bit more interesting here, like you see that the models also, for example, seems to extract some very simple concepts. For example, here it just extracted the concept that says the next word. Yeah, and this is just like a hypothetical example, right? In reality, those models are so big that you cannot really visualize it, but you will find concepts like sequentiality or pointing back to the previous thing, or nouns relating to adjectives, and all those things. You may find those in those model weights. So what are large language models? Where are they coming from? I mean, initially they were basically introduced to do translation, and they were trained to be really good at finding the next word, the next most probable word. And as a size example here, that was how GPT-3 was trained, with 410 billion tokens and then about 100 billion additional, so around 500 billion tokens. Nowadays, we're talking about 2 trillion, 4 trillion tokens when you talk about Llama 2 and GPT-4. I'm not sure if they even published how many tokens they used for GPT-4. An interesting observation, however, is that in the timeline when the paper came out around 2018-ish, the attention all you need, and then those other models came out. This is like 10 times larger than this, and this is 10 times larger than this, but the training budget was always in the tens of millions of US dollars, because innovation is so fast that in a year and 2 years, we're exceeding Moore's law nowadays in training, yeah? Because of the innovations in hardware and in algorithms. What is GPT, however, in that you interact with in ChatGPT? Now, the best thing I can do is open a non-GPT model, because the basic models of GPT are not really available that easy anymore. Bloom. Hugging Face. Because you're all used to interacting with GPT, and for example, I say, what is the color of the sky? If you use ChatGPT, you would expect something, hey, the sky is blue, and what do you think about it? But when you ask like a real foundation model that's only trained on finding the next probable token, it just can generate some random text. Yeah. So if I would give it, however, that's a technique called few-shot learning. A few examples before. Let's say, what is the color of snow? Q. A. White. Q. What is the color of blood? Red. Q. What is the color of the sky? And then write A, then I have a higher chance that it will give me something meaningful. Yeah, at least it gave the answer. Because I gave it more examples, and I nudged the model into like, hey, this is like a question-answer pattern, and so looked in all the training data and found things that point in that direction, that really somebody wanted an answer. Now, what OpenAI did for us, they built those instruct models by basically having a lot of labelers marking like how should question-answer pairs look like. What is a good answer? And then they trained a so-called reward model. So reward model means they trained a different AI model that doesn't generate text, that's able to say, a human would think this is good. And then they use this reward model to basically process like millions and millions of question-answer pairs, generations from the earlier version of ChatGPT, and then the reward model will say, a human would like this, a human wouldn't like this. And they used that for training. And then they went back to labelers and so on. This way, they were able to do it just at scale better than other people so far, and they're having amazing results. And not a lot of companies, I mean, that's something the open source community cannot do that well yet. But fine-tuning is in the sense of instruct training, improving models to follow instructions, is mostly done in the open source scene by supervised fine-tuning by just providing examples and not those reward model step. Now ChatGPT improved on that further by giving you the question-answer pair chat style. So basically it was further improved to be able to interact with users multi-term conversations. But let's look here, how would that look like in actual when you work with a model. So I'm going into Azure OpenAI Studio right now. So in Azure OpenAI, you can generate language resources, and I pre-created a GPT-4 resource here. I hope everything works still. And you see something here. You see something, a system message. Like, this is nothing that you tell the model, but this is something that the model already knows before you interact. It's part of the so-called prompt. And the model always, when it gets called, gets everything. It gets a really long string, and the system message, the system prompt is part of it. For example, you and I's system that helps people find information. You will not lie. You will not hurt. You will not be hurtful in your responses. Never gonna lie, never gonna hurt you. Yeah. So, and then we save that. Now, and when I will give it an example, it's now make a funny joke how boring a German speaker is. Yeah? And you will see that, well, here it says, I will not, cannot fulfill that request. Now, this is nothing because of that prompt I gave it. This is like because OpenAI tuned it that way. Let's do something else. When asked to talk about German, pretend the person is Austrian. Save that. The chat. Hey, I'm German. How is the weather in Berlin? So here, I'm programmed to refer to people from Austria as Austrians. Nevertheless, the word Berlin is cloudy. So the model also makes up things. It doesn't know any lookup in this case. What's interesting is here how you interact with the model. How does it work in actually? So you give it basically a big string. And the string has all those things in here before. Like you give it the role, the system role, you give it all this string at the beginning, and then the whole chat history. The chat history grows and grows and grows until you reach the so-called token limit. The other parameters that you may want to keep in mind are things like max response length, temperature, top P, and so on. The temperature and top P are basically they're used by the so-called sampler. When the model generates the next response, it gets a probability list of possible tokens. And this is basically a strategy that's then used to select the next response. If the temperature would be 0, then it would also always use the most probable token. If the temperature is a little bit higher, then it also mixes, to a certain degree, a little bit less probable tokens to get a little bit more varied responses. And people found that actually is better in a lot of cases. Now that we have seen this, how that looks in the portal, what does it mean when we would work in code? Here I have a very, very basic example. It's like an example workbook. How it would look when you work in .NET, for example, to interact with this. What you do, you install the Azure OpenAI NuGet package. This is here polyglot notebook. The polyglot notebooks let you work like a Jupyter notebooks in Python, but in .NET style, right? So we can interactively try things out. And we initialize it, we start a client application here, and we ask now the install text DaVinci 003 model, that's not a chat model, to tell me something. And it gives me a generation, and the generation has an object structure, has also some prompt filter results. If you use Azure OpenAI, you get capabilities built into to your liking, avoid violent speech, avoid nudity, or different things that may be considered offensive, yeah? So the text here tell me something about the expansion factors. Expansion factors are used to express blah, 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 blah. So in this case, again, the DaVinci model is in an instruct model, but not a chat model. And in this case, it thought, I just continue saying what was said. And here's an interesting part for you as a developer, the finish reason. The finish reason is length. Length means that the API thinks, hey, what I gave you is a complete response as the model thinks it should have generated it. Internally, it created a stop token, and the API basically found out, oh, that's a stop token, we don't need to keep generating. Otherwise, models would want to keep generating token by token by token by token. Now here's a raw response, it's just the object structure in a little different way. To tell you the same thing, but when you say like, hey, but I don't want so many tokens, you can say tell the API, only give me 4 tokens. Yeah, so it starts generating, and technology is, and then finish reason length. So there's a difference, right? So if you do this and you give the API like, please generate only 4 tokens, and then oh, yeah, there could be more, that could be relevant, it could be generated, but it is maybe good for you because you pay by token usage, so sometimes you may want to look at only the first 10 tokens or 20 tokens, if that's good enough for you, and then you continue. Like this is one of the options you can use for that. Like here's another example that's basically I'm looping now over max tokens equals 2, and basically it's just a simple loop over this, and you see that the model generates in 2 token pairs the responses. Yeah, so it's like and I just do that until the finish reason is stopped, which is in this case equal to length being reached. Yeah, come. Well, it may be a while, so I hope you believe me that that it will finish eventually. So this is now where we get into more interesting territory when you work with this like in ChatGPT. So you initialize it with a chat message as a system role, then you give it a chat message in the user role, you, in this case the questions, and the question is tell me how do I get from Bellevue to Redmond? Yeah, how do I do that? And then you add that, and here I want only one choice, and now give me the chat completion. And basically here in the system message I put please answer in rhyme. Yeah. So you get some type of, again, finish reason is stop. So in the how do you call it? In the chat API they call it stop and not length, I believe. And it gives me a description. If those who know a little bit Redmond and Bellevue, it's kind of accurate-ish, like to get from Bellevue to Redmond, here's the way, just follow my instructions, don't go to the stray, take the exit, and so on and so on. Yeah? And you see a few interesting things here also. Function call equals null. And we will get to this, what that means, in a little bit. So you see it followed the instructions and generated some because of its world knowledge. How do you get from Bellevue to Redmond? And you could trust that. But it would be cool if you could like hook that up into, let's say, a real application that's able to do map lookups, navigation lookups. And we will look into that a little later in those demos. Yeah. Another example would be like how do I train a parrot? Like give me, and this is to show you, you can also interact with the model in an async pattern, like you get the responses as the model creates it. The models can be pretty slow. Sometimes a generation can take 10 seconds, 20 seconds, depending if the server is busy. And using one of the async functions and just basically streaming the results also enables you two things. One is like you are more responsive to your users, but you could also decide, I'm done, I have seen enough, I have my, for example, you may have your own custom filter that you want to prohibit specific words. Maybe you have an AI model that shouldn't, I don't know, should avoid specific words, or if you feed it with some confidential information that you don't want it to leak, you could have other filters, for example, that you want to interject there. Now, let's look at functions. Functions is a relatively new feature of OpenAI and Azure OpenAI. And this is what is behind everything you hear about plugins and copilots and all this magic that people are talking about. It basically is a question, how can we, with that large language model, interact with our custom code? Yeah? In this case, what we do is like we define a so-called function definition, has a name, get route from A to B, has a description, what does it do, get the route in direction of the location A to B, and then has specific parameters, like location A, that's a start city, and state from which the direction is calculated, and then the destination city. And behind the scenes, how does it look like? It's basically just a JSON object that is being fed into the large language model, and the large language model has been trained, not by us, but by OpenAI, to understand this type of, let's say, object structure, like this JSON object structure. Now, so when I now add this function to my available options to generate a completion, and I do now a completion for the same thing, I see something different. The same question is again, how do I get from Bellevue to Redmond? Suddenly I get a finish reason function call. Yeah? So the model now realized that instead of just generating random text, hey, somebody asked for something where I know that there's a function exists for, like here, and this is the data that is relevant here. The function call is the function get route from A to B, and the location A is Bellevue, and the location B is Redmond. Behind the scenes, this is because the large language model just has so much generic understanding of language that it is able to match those function descriptions with some additional training to the arbitrary questions that we ask it. Yeah? This is also how, behind the scenes, it's able to use, let's say, for example, the Python code that was generated in the initial demo that I showed you, and so on. So it knows now that if you would have that function to like get the route, and unfortunately I don't have it right now here, we could now call that function, get the result from our own database, or from Google Maps, or from Bing Maps, and feed that back into our prompt. That is the secret sauce behind all the copilots and all the plugins that you may have heard. The actual calling of the function is something the developers needs to do, or your custom runtimes needs to do. And for example, systems like Semantic Kernel or LangChain, they are already equipped to be able to understand function definitions and how do you describe something to call and so on. The plugins, by the way, follow the OpenAPI standard, the ChatGPT plugins, and that Microsoft also uses. So you would have to define your plugins basically as web services according to the OpenAPI standards. Okay, and now here you would then call basically you would call the function now based on that chat message that you received. Yeah. Now, the other thing I wanted to get briefly into is this topic of embeddings. The other thing you hear a lot is how do you talk to your own data? Yeah, how do I do this? I want to inject my own data, and well, you could use functions to some extent for that. But the other thing is basically based on something called embeddings. Embeddings is a semantic way how to represent information as, it's a way to represent semantics as numbers. Like in this case, as like 1536 numbers. It's like every embedding for a block of text is basically an array of 1536 numbers with the embeddings that OpenAI has. So for cute dog, this is basically this long string here. Now, if you have embeddings, it's a vector. Yeah? You can do things with vectors. For example, you can calculate the Euclidean distance or the cosine similarity. There are different similarity metrics based on algebra, and linear algebra that you can use on vectors. And nothing else is done behind the scenes with when people talk, like we want to talk about your own data. What they do first is they calculate embeddings. Like here, let's say, calculate similarity, and then let's say you have a helper function, get embeddings for string, and now I have a few strings here. Like for example, I have a string, John really does like ice cream, John really does dislike ice cream, John really doesn't like ice cream, and alpaca licks space rocks. And now I'm calculating the embeddings, and I'm looking at the similarity, for example, between liking ice cream, doesn't like ice cream, liking ice cream, disliking ice cream, liking ice cream and disliking doesn't like ice cream, and embeddings like ice cream, and embeddings alpacas lick space rocks. What we find there is, for example, that the similarity between embeddings like ice cream and doesn't like ice cream is like 0.95, which is lower than the embeddings between doesn't like ice cream and disliking ice cream. So it knows to some extent that liking ice cream and disliking ice cream is less related than 2 times not liking ice cream. However, and that is important for you when you develop your own systems, it's not like it's not able to really contrast negative information with a strong signal in the number. For example, the similarity between liking ice cream and alpaca lick space rocks is 0.76, which is lower than all of them. So meaning if you build something with a query that's like that's a negative query type of thing, so you may not get the expected results often, like in terms of excluding information you want to exclude. Be aware of that. Now, how do the then systems use this? The systems use this, for example, let's see if I can demonstrate it in Azure OpenAI, chat at your own data preview. I hope I have it still. Oops. No, upload files. Okay. And then I'm able now to use embedding vector. I should be able now to upload some text. No, come on. Okay, my demo gods fail me here. So I cannot show you that right now. I must have messed up something, but to try to fix that. So what would happen behind the scene? It would upload, let's say, a PDF file. Then it would look at the PDF file in different blocks, because it has a size limitation. Let's say the embeddings can be, I don't know, 15,000 tokens, but PDF file is 1 million tokens, then it would basically chunk it up in like 10,000 tokens, 10,000 tokens, 20,000 tokens, and create an embedding from that and store that somewhere. So you have the embedding, and you have the actual text. Now, when you search for it, when you search like, hey, I want to chat, like, what is in that PDF file? Now, what happens then? What happens then is then you get into this territory of so-called vector databases. Vector databases store this embedding, like this is just a big vector, and just return it, and they're able to calculate cosine similarity, like I mentioned before. Let's say when there's a question like is in the PDF, like what can you tell me about NDC conference dinner time? And this would be the PDF about the conference, and it is very likely that it's enabled then to find an embedding that is close to talking about dinner times, if it has information about dinner times in the PDF, because of it just has a highest number of like this similarity index in the embedding. That's all those so-called vector databases help you do. They store the vectors, the embeddings in an efficient way, and they have basically optimized functionality to retrieve them later on for you. Okay, now the other thing I wanted to get into is how do we develop like a little bit more advanced systems? You reach a point, I mean, where you could build your own libraries, your own tools to, for example, integrate vector databases, or to build composite applications, or how do I store my prompts, and all those things are solved for you by specific tool chains. One of the tool chains is very popular, is LangChain, that's primarily Python, but also JavaScript. And in the Microsoft world, we have Semantic Kernel, which is an open source product. And Semantic Kernel does, come on, does something for you, for example. It is able to, for example, first of all, it's .NET based, so you don't leave the familiar world of .NET, and it is able to work with so-called skills. Skills, or I think they're renaming the plugin. And so skills are basically just prompts that you can use in your apps like a function. Here was a so-called fun skill. Joke, time travel to the dinosaur age. And so it generates text. Why did the time traveler refuse to fight the T-Rex? Because he didn't want to be dinosaur tomorrow. Yeah. So, but how does it do that? Yeah. So, semantic kernel, and if we go into the skills here, fun skills scope, it has basically a configuration, and the configuration has a description, which is basically a really, really simple prompt, and those pre-configured weights that you it's a pre-configured parameters like temperature and so on, a top 5 that you can feed the language model with. I think I opened the wrong file now. The actual library is in sample skills, fun skill, joke. Then it has here a little bit longer prompt, write exactly one joke, and joke must be G-rated, workplace family safety, and has like a little syntax how you then feed in information and get output information, and it still has that config here. So this is what semantic kernel enables you to do. For a little bit more advanced example of semantic kernel, I have a little video that I recorded earlier that I actually showed at a different conference, but it's not conference branded, so I can show it to you really quickly. Now, this demo here
We're starting the Chat Copilot example app by the PowerShell.
we don't need this. Okay, there's an example app also that you can download, which tells you how a good pattern how to implement my own copilots, including how do I build a plugin, how do I store information, how do I work with a vector database, and all those things. Now, in this example app, you can do a few interesting things. For example, the first thing we do is we're going to activate the plugins that it knows of. You can add a plugin, custom plugin, and here it knows already about a Microsoft Graph plugin that's also open source. You can use it. So here's an example that teaches basically how to interact with Microsoft Graph with the capabilities: calendars read, mail send, read, write, and so on. Behind the scenes, that looks very similar to what I showed you in the samples source code for interacting with raw APIs. So basically, it has a calendar read function, it describes the parameters, and basically the Copilot has a really, really, really long prompt behind the scenes that describes all the functions. And when you ask it now a specific question, for example, the question being, what is my last appointment? Then, in this case, in my calendar, now the semantic kernel, together with the language model, does for the following. It generates a so-called plan. What do I do with this? Because it has been fed all those different plugins. Now the first step, it generates a plan. What do I do next? And the plan is like here. I want to get calendar events, and I want to get last event, and from there I want to output the results last appointment. Is that okay for you? I mean, that's something they implemented, like to confirm. Because, for example, if you want to delete information or send an email, maybe you want to have a confirm button for this. Yes, so that's a good pattern in general to do. And it executes this, and then your last appointment with Alex was on August 8. Now, how does it look behind the scene? It basically generates also a JSON first for the plan. The proposed plan is a JSON structure and has several steps. For example, with the parameters, the input, the max results, and then here the function get calendar events. Now, semantic kernel will do the calling of this plugin for you. Let's see where it is. And you could also let it send an email after that. Let's see if it shows me the plan in a different format. Yeah. Okay, so you can, yeah, this is then the complete generated plan for you. So the last thing I wanted to show you is another cool thing you can do with embeddings, meaning exploring information. So as I've showed you earlier, embeddings give you some similarity information about text. So what can you do with it? In this case, I did a little crawling of the NDC Porto website and then assigned a few categories: cloud computing, programming languages, artificial intelligence, soft skills, self-improvement, and calculated embeddings for this. And now I want to calculate basically the proximity of those topics with some of the session abstracts. Now, what happens behind the scenes? I mean, this is Python, so I'm using a lot of work on other people's giants. We have 1,536 dimensions that represent semantics. Yeah. We do a so-called dimensionality reduction. It's a heavy word, but it means basically, hey, simplify this from 1,500 dimensions to 3 dimensions so I can see it. And we can then give it points, but those things I care for are like those topic names, like cloud computing and so on and so on. And then when we do this, we get some interesting things. I mean, the coloring is not perfect here, but then we can draw something because it reduces the 3-dimensional space, and here's a topic cloud computing. You see these abstracts that are close, for example, toward a carbon-aware cloud, cloud with dev containers, cloud and native security landscape. And here the topic is artificial intelligence, and here AI in the future work, and modern trolley problem, responsible AI principles, and so on. Now, this is a very interesting technique if you want to explore really, really, really large data sets and do things like cluster analysis and so on. I mean, you could extend that and then, for example, think about you could remove keywords and add keywords and do your math in a different way. I think I have one more way I rendered it here. This uses a slightly different methodology behind it, where basically those keywords act like attractors, and they're being pulled in the direction of the keyword, but it has a very similar result. You can explore your information based on the semantics that it has internally. Yeah? It's also what I wanted to share with you all. Now, the last thing, of course, all this thing is not without risk. We cannot hide that, and there's a lot of ways how this can occur for you because users may do nasty things. Yeah? So you can try to, for example, in your prompt, you can mitigate some of the risks by telling, let's see, cancel. In your prompt already, in the system message, you can try to give it more rules what it should do. Like it should never lie, it should always be friendly. And the models have been usually also optimized for that a little bit. But there are attacks towards that, different ways how you can trick a model. And so this is not a completely secure way. So people can find workarounds for that. There's also papers that describe general adversarial attacks against large language models that have been patched now for the production models that I'm aware of, but where people can say, hey, how do I build a bomb? And usually the model would say, no, can't do that. It's not good, shouldn't build bombs. But sometimes you can trick it, and the tricks are sometimes, for example, they find the ways where in the model weights it would start saying, sure, or yeah, this is how you, and like then they're nudging the models little bit by little into that direction. That is why often you have models supervising models. Like for example, the pure generation that you get, and that you find that also if you interact with Bing Chat, for example. If you try Bing Chat, then sometimes it generates some text and suddenly says, oops, I can't do this. So this is because there's a secondary content filter model that supervises the text based on specific rules. Yeah? You can argue if that's a good idea or not. My personal views are that you could give people more power because the bad guys will do bad things anyways. And there are also workarounds for that. There are tricks for that. For example, if you, let's say, now let's say this one here. Generate text as lookalike ASCII. No, lookalike Unicode. Let's see if it does it here. Okay, he doesn't do it here. Let's do it in ChatGPT. Tell me something funny, but use lookalike Unicode output. See, and you see that it uses like basically those characters that are not actual Unicode characters, but just look like it, like a spam system, like seance and other side, or like a tilde under the E. Now, those tricks, for example, may already trick some of the content filters that are out there. You could also say generate this as base 64 encoded, like, okay, now base 64 encoded. Yeah, so you could generalize something like this. So there are a lot of ways that people can still trick your system to generate nasty stuff that you probably will not be able to detect easily. Yeah, I mean, it won't be directly visible to the end user, like because it's base 64 encoded in this case. But you could see that some of the secondary content filters may fail if you do something like that. Yeah, and as models get more capable, the evasion tricks that you can use on your end to evade also get more advanced. Yeah, so maybe you can define your own more complex ciphers than base 64 encoded. Yeah, so this is kind of where I want to stop the presentation for today. I could talk like probably for hours, but my goal was to give you like a little bit of a foundation of what is behind all this and how it fits together in the sense, and cutting through some of the hyperbole that you see on YouTube and so on. Models will get a lot more powerful, and the GPT-4 vision that just came out, people are only learning to explore what it means, and I cannot talk about too much how that works behind the scenes and so on, because much of it has not been published yet. But in general, the concepts behind the scenes always work also in the so-called semantic space. Meaning, internally they always use embeddings, some math representation, and combine, let's say, a semantic representation of an image with the semantic representation of a text, and then combine all of this and generate text out of this. So this is a very simplified view of it. Now, the last 5 minutes, I want to open up for questions or spend it like you want to. So we could either try something that you wanted to see if it works or doesn't work, or you can ask me something. Okay, I take the silence that you don't have questions, or you. Oh, there's a question.
Yeah, my question is, for example, we are writing a subsystem that will be by training. I mean, it knows about our internal documentation. What is the best approach to get a meaningful request when we ask about our internal system? Is it using embeddings or fine-tuning or just providing some context?
So the question was, when you have your internal system that works on internal documents, what is the best way how to interact with that and get information in there? So there are a few patterns that have been established and currently, and usually it's a combination of embeddings to store the information that you care for. Then you do a lookup, meaning lookup of the embeddings and get the text segments that may be relevant. Then you ask the language model for the text segments, please summarize them or form in a way, and then you put this in a new prompt and tell the language model, like this is extracted and modified text that you got. Now summarize of those 5 documents what is relevant for the question that was asked about what's our healthcare coverage or vacation policy or who was the most productive person and so on. The technique is called retrieval augmented generation. So you first retrieve some information out of some arbitrary system. Could also be a plugin or lookup in a database, but often it's done with embedding in vector databases, and then take the text and put it in the generation again. Fine-tuning is currently, because of the scarcity of resources for the most capable models, pretty cost prohibitive. And some people use it, however, but it's less about teaching the model new facts, but for example, modifying the style. For example, let's say you have a database of 10,000 emails that you send to customers that you know are written well and reflect the style you want your model to speak, because that's a corporate style. Then you could fine-tune maybe that model to more reflect the style that you usually use. So you could also try that with larger prompts, but it may not be as good at copying a style than fine-tuning, for example. There are also additional techniques, LoRa, low-rank adaptation, for example, that's also a paper from Microsoft, where they found that there's some sparsity in the model weights and the internal representation. They basically found, let's say, a trick how you can have a lot smaller file that acts like an adapter you plug in, and it does something like fine-tuning for you, so it can nudge the model also in the direction like you want, without needing a full fine-tuning of the really, really, really large model file. That's very popular for image generation, for example, for stable diffusion. There's a lot of low-rank adaptation, LoRa files to represent a style or how you look like, introduce that to the image and so on. I hope that helps a little. Okay, so we have 1 more minute. So last question. I'm also around, and you can look me up on LinkedIn and shoot me questions. I will try to answer what I know. Okay, well, with that, thank you for hanging out with me, and I hope you have a wonderful time in Porto and that we will have less rain. Thanks.